Have you ever been playing a game or watching a digital simulation and just stopped to marvel at the swirling sparks of a massive explosion, or maybe a terrifyingly realistic swarm of thousands of insects? We kind of take these effects for granted nowadays, but behind the scenes, there is a fierce computational battle going on. So let's dive into this explainer where we're going to uncover the staggering math and raw GPU power that literally brings modern digital worlds to life. Today, we're unpacking exactly how graphics hardware achieves this illusion of life. I mean, just think about the chaotic, spectacular beauty of these systems. We aren't talking about a pre-rendered video here. We're talking about millions of interacting particles running entirely on the GPU in real time. We're going to learn exactly how video games and simulation engines render these massive swarms and interactive explosions without, completely melting your computer's hardware. And it all comes down to a really fundamental shift in how we tell computers to draw tiny, moving dots.
All right, Section 1, the GPU particle revolution. Let's see how these systems are finally breaking free.
So, to understand how we actually get to millions of particles, we've got to zoom way into the microscopic level. See, for years, digital particles were driven by what we call parametric systems. Think of a parametric particle like a cart on a mathematical roller coaster. You know exactly where it's going to be at any given second because its entire path is strictly dictated by an equation of motion. But non-parametric systems, they change everything. They basically turn those roller coaster carts into actors on a stage. These particles actually have a memory of their previous instantaneous velocity and position. And because they remember where they just were and how fast they were going, they can dynamically react to the world around them by integrating equations of acceleration.
It really boils down to this comparison. Parametric systems use exact analytical equations. The upside, zero extra memory. But the downside is huge. If an object gets in their way, they can't react. Their motion just cannot change in real time. Non-parametric systems, on the other hand, integrate acceleration over time to compute their instantaneous velocity. Sure, it requires a bit more memory to hold those states, but you gain the ultimate flexibility. Suddenly, these particles are literally alive to their surroundings.
Moving right along to Section 2, breaking the predestined path. This is all about memory and continuity.
Okay, so our particles are off their tracks, but to actually make this work, the GPU needs to remember where every single particle was in the previous frame. To hold this memory, the system stores the data in vertex buffers or massive 2D texture arrays. But of course, there's a catch. Programmable GPU pipelines don't actually let you read, modify, and write to the exact same piece of memory simultaneously. You can't just look at a particle's position and update it in the exact same spot in one go. So engineers use this super clever double buffering trick called the ping-pong technique. The system reads the old state from buffer A, does the math using Euler integration to figure out the new velocity and position, and then writes that fresh data over to buffer B. And in the next frame, they just swap. Buffer B becomes the reader, and buffer A gets written over, just back and forth, ping-ponging millions of times a second.
Now you might be wondering, how do we alter a particle's behavior without it looking terrible? Well, if you instantly change a particle's position, it snaps, right? Like teleportation. That breaks what mathematicians call C1 continuity. If you change its velocity, it visually jerks, breaking C2 continuity. The real trick here is altering only a particle's acceleration, which breaks C3 continuity. Doing it this way keeps the visual transition incredibly smooth to the human eye. It avoids those jarring visual skips, even when a particle suddenly decides to turn completely around.
Which brings us to Section 3, flux, swarms, and gravity. Let's solve some n-body problems.
Let's zoom out a bit from the individual particle. What happens when millions of these individual actors need to flock together? This is where we hit a massive computational headache. Think about a swarm of bees. If every single bee needs to check its exact position against every other bee to avoid a crash, you hit a classic n-body problem. If you have just 10,000 particles, that is 100 million calculations per frame. How on earth does the GPU handle that massive workload in just a few milliseconds?
The workaround for this is absolutely mind-blowing. It's a technique called force splatting. Instead of doing complex spatial math, the GPU just leans into its raw rendering power. A quad primitive, which is essentially just a simple flat square, represents each particle's area of influence. By rendering all these overlapping squares and using additive alpha blending, the GPU effectively stacks up all the repellent or gravitational forces into a single combined texture map. It essentially splats the forces onto a canvas, accumulating the total push and pull on every single point in space instantly.
Pretty genius, right?
But swarms don't just avoid each other. They also group together and align their directions. To simulate these advanced flocking behaviors, things like cohesion and alignment, the GPU needs to know the average position of the whole flock. Now, instead of adding them all up one by one, the GPU uses incredibly fast texture averaging by generating mipmaps on the fly. It basically shrinks the velocity or position texture down by half, over and over, until it's just one single pixel. And boom, it instantly finds the flock's center of mass or its average heading. It's just a brilliant hack that uses traditional graphic tools for really complex physics.
Okay, Section 4, Colliding with the World. Let's talk about volume textures.
Having particles react to each other is super cool, no doubt. But for true immersion, they need to react to the 3D environments around them, not just simple spherical point charges. To solve this, the system uses geometry shaders to essentially chop 3D space up into a grid or a volume texture. Imagine taking a whole scene and breaking it down into tiny little 3D cubes. The system stores the surface angle or plane equation of the actual 3D model inside those specific cubes. This is exactly why your game character can walk right through a digital waterfall and the water actually bounces off their shoulders. The water particles fly into a 3D grid cell, check the data, realize there's a shoulder intersecting there, and physically deflect.
But here's the catch. Modern digital models are insanely detailed. What happens when highly detailed geometry squeezes multiple different surface angles into the exact same tiny grid cell? Storing all of them would totally crash your video memory. Well, the GPU smartly saves memory by resolving this aliasing. It looks at the direction the majority of the particles are traveling from, say a waterfall falling straight down, and it only keeps the plane equation that is closest to that direction. It literally just throws away the interior angles the water would never hit anyway.
All right, Section 5, Leaving a Mark. Time to do some painting with particles.
Now for some real magic. We want these dynamic particles to actually paint, burn, or damage the environment they collide with, like physically splattering color onto a 3D creature. To achieve this, the GPU basically flattens the 3D model out into a 2D map, rendering its world space position directly into a UV texture buffer. With this flattened map of exactly where every part of the monster is in the world, the GPU can incredibly quickly gather up any intersecting particles. When a particle hits the right spot, the system permanently splatters its paint directly onto the object's surface texture. The particles actually leave a permanent interactive mark.
Which leads us perfectly into Section 6, the future of fluids and adaptive hybrid grids. So all this incredible foundational math, it paves the way for the mind-blowing, hyper-realistic fluid dynamics we're seeing in the latest simulations. Researchers didn't just stop at standard particles. Modern frameworks like the Cirrus framework now combine the absolute best of both worlds. They use an adaptive hybrid approach. They use a grid-based system known as Eulerian tracking to monitor the broad, long-range flow of a fluid across a coarse space. Then, they inject our non-parametric Lagrangian particles inside that grid to track the incredibly fine, high-resolution short-range details and impacts.
And let me tell you, the results of smashing these tracking methods together are just astounding. By optimizing this hybrid Eulerian Lagrangian approach on modern hardware like an RTX 4090 GPU, today's simulations can achieve a staggering effective resolution of 512 by 512 by 2048. We're talking about a massive hyperdense grid of data. That yields efficiency gains of up to 2 orders of magnitude while providing fluid dynamics that look, frankly, virtually indistinguishable from real life.
So, that leaves us with a pretty provocative thought to wrap things up. We started with a single particle on a predestined path, and we've ended up with massive adaptive grids computing billions of interactions in fractions of a second. If this is the staggering scale of interaction in physics we can compute in mere milliseconds today, what level of reality are we going to be generating tomorrow? Thank you for exploring the illusion of life with us in this explainer. Keep your eyes peeled the next time you see a digital explosion, because now you know exactly the kind of mathematical magic happening right behind the screen.